invite you like 10 times.
Do you have any more syllabuses?
I've got a couple more. Yep. How many short? 5 up there.
I've got 3. Let me see if we can track down 3 more. We have any extra syllabus copies floating around? We're missing a few over there. No. All right, we got more than our enrollment. If you don't end up with a copy of the syllabus, it is up on Icon. I uploaded it last night, and for some reason it was this weird, like none of the revisions were approved, so it was this marked up mess. The one online now is all good to go. So if you don't get a hard copy, you can find it there. It looks like we got a few more people than the enrollment size, so we're like short a handful. Look on Icon, I have I wasn't going to print them out at all, just to save paper, but I'll run through the major points and then you can find out. I'll print out a few more for the next lecture. I'll double check that there's like 5 different published layers, so I'll make sure that it's published right after lecture.
Gotcha. Anything that's syllabus like really important to me for like today, or is it just?
No, I'm going to run through the main points. I'll bring a couple more copies on my schedule.
Okay, cool. Thanks.
All right. Welcome everyone to Fluids. If this isn't the we don't have any projection. Okay, hold on. There we go. All right. If that's not the course number you expected to see at this time slot, now's your chance to exit gracefully. I did hear somebody asking what class this was as they filed into the room, so make sure you know. I'm Professor Harwood from the Mechanical Engineering Department, and today is going to be about half and half preliminaries, logistics, talk over the syllabus, sort of what we want for this class, and then get into some of the very first, bits of actual material. So, as I said, I'm Prof. Harwood. My email is up there. Course, right? You clearly all know, meets Monday, Wednesday, Friday, 11:30 to 12:20. My office hours right now are scheduled for the hour immediately following class. So 12:30 to 1:30 p.m. over in my office at Siemens Center, which is 3139. In addition to these office hours, we are going to have probably 3 or 4 TA office hours each week. Those times we've had a little bit of a snafu with TA allocations, so those will be finalized in the next day or two, and I'll get those out to you as soon as we know exactly what those TA hours are going to be. The course website, the icon site, shown there. Somebody mentioned that the icon site wasn't showing up yet. Right after we're done here, I'll go make sure that everything's squared away and that's published, so you all have access. So, a couple of things about this course. All right, those of you who have friends in the year ahead of you might have heard whispers of some problems I've had in the past with online solutions resources and such. One of the things I want to be clear about is in this class, I'm dead set on maintaining academic honesty because it's going to help you guys. And I know I can say this 100 times, and it always seems to fall on deaf ears for a few. Okay, but the homework solution sets are not here for my enjoyment. I don't enjoy grading those, personally. But they are here to be your chance to make mistakes, learn the process, so that when when push comes to shove on the exams, you know the material, you can do well. All right. So please, please, please. We all know the solutions manuals are floating around. They're not hard to get a hold of. Ignore them. Okay. Don't go there. Come to my office hours. Come to the TA office hours. If it comes to it, email me. All right. There are resources available to help you get the material. Please do not cheapen the experience and hurt yourselves by going to third-party solutions. All right, and there's an element of self-preservation here. Shown here is a snapshot from the user policy of one of the really popular websites, Chegg. Okay, there are similar policies for Course Hero, Quizlet, lots of these online solution services. And this little highlighted portion at the bottom is something that a lot of people don't seem to know. All right. Essentially, what it's saying is that if you as students, post or use solutions that in violation of your institution's academic honesty policy, okay, that your account information can be handed over to the school. All right, and this is something I've done in the past when I found a lot of problem sets that I had written, okay, and quiz problems that I had written posted online to Chegg, because they actually handed over a list of names of people that had accessed those answers. Okay, so I don't want to kill the mood in the room here, but just a word of warning. All right, moving on to the course schedule that you see in your syllabus. Shown here is a little snapshot. It's in the third page is where this starts. We've got the course broken into modules, which roughly correspond to the chapters in the book. Also, if you go online, each of these modules is going to have a list of sort of learning objectives. Like, we want the students to know this by being able to do this, and use that as your kind of your study guide. That's the end-all, be-all of the things we want you to get out of this class. And the schedule is the way we plan to deliver that content to you. On the far right column, okay, are the homework assignments for each lecture. It's going to be 2 or 3 practice problems. The idea is you take these, for today, for example, we're in the Introduction to Fluids. This is an old schedule. This is from the spring semester, so ignore the MLK Day. But today we're talking Introduction to Fluids and the homework assignments 115, 118, 139. Okay, the idea is take those, you do those, scan your solutions, and upload them to the icon Dropbox. That'll be open. And so we're going to do all the homework tracking, grading, and returning of scores through icon. It makes things faster, and it leads to fewer misplaced assignments, late turn-ins, and such. Okay, so let's get into what's actually going on with this class. Right? So before we start, right, we've all got some idea of what fluids is. Personally, this is my favorite topic. It's a hard topic, but it's a really, really rich one. There's something in this for everybody. Okay, I think I have a little blurb about it in the syllabus saying, right, fluids is pervasive, right? It's what allows us to design airplanes, keep skyscrapers standing up during windstorms, even down to sizing of stints and and medical implantable devices for circulatory health. Okay, it's everywhere, and so that's why we have a mix of, I think, mechanical engineer, biomedical engineer, civil engineers. Let's get a show of hands, actually. How many MEs are in here? Okay, CEs and BMEs. Okay, so we're an ME heavy crowd. Well, don't worry, you other folks aren't going to be left out. So we've all encountered fluids. This is really the first time, though, that we're going to be asking you guys to quantify it. So this is going to take elements of your work in calculus, namely like multivariable calculus and vector calc. It's going to be taking those. It's going to be taking your thermodynamics experience, open and closed systems, some of your chemistry experience, right, ideal gas law, etc., and mashing those all together into how we describe the way fluids work, both qualitatively and quantitatively. So small little class activity first, before we get into any of the actual lecture. I want you guys to take 2 minutes and sort of formulate and write down some question, okay, open-ended here, some question having to do with fluids that you have noticed or asked yourself in the past or would like to try to answer with this class. Okay? I want you to write it down and you're going to save it, because at the very end of this class, for a grade, you're going to come back and you're going to try to answer that question. Okay. Yes.
And then on the exams here it says midterms will be on
Okay, I think we missed fixing it
and
there.
then
It's going to be...
it's at 6 to 8?
Yes.
Okay, because also on my UI it says 6:30 to 8:30.
6:30 to 8:30.
And then this says 6 to 8.
All right, we'll figure
I
that
just
out.
put like writing
I put in the
it down
request
and I
for
was
6 to
like,
8,
okay.
and I'll make sure to get that cleared up in the next 24
Thank
hours.
you.
Yep. All right, assume you got something written down. I want you to take the next 2 minutes, and we're going to do a lot of these little pairing off activities, right? So whoever's sitting next to you, explain your question and how it came about for the next 2 minutes. All right, I want you to try to vocalize this. Okay. So hopefully we've got a range of good queries, and we're going to try to hit as many of those as possible during this class. So I want to share with you a little bit kind of what my questions are in fluids. We'll come back to this in just a moment. So my background, right, as a researcher, as well as when I was a student, was in, let's get this going, was in marine hydrodynamics. That is, the fluid dynamics associated with ships, boats, propellers, hydrofoils, etc., things in an ocean environment, which is a really weird thing to study in Iowa, right? But it turns out, right, most of you have seen the IIHR building across the river from the power plant. This is actually sort of a cornerstone in fluid dynamics in the U.S. for the last nearly 100 years. And a big part of what we do is in marine or naval hydrodynamics. We have a towing tank in the basement over there, a 300-foot long tank of water to test model boats in. We have a wave basin out in Coralville, which is a even larger tank of water. It's rectangular, about 800 square meters, that you can run robotic or radio-controlled models in while making waves. There's a big robotic tracking system, uses cameras and lasers to track free-running models. What I've done work in the past has been everything from testing of platform demonstrations. So in the upper right there is some work I did out in Honolulu on a 50-foot long patrol boat where I think my spine was compressed for about a week after that hit right there. Or in the lower right, work I did on hydrofoils and multi-phase flow out in Italy in 2016. This example here having a lot to do with what goes on in the dagger boards or foils on things like the America's Cup yachts, if any of you are into sailing. But it also extends to more practical everyday things like shipping of containers, right? 95% of the world's goods travel by sea, and a vast majority of those go in these boxes on these container ships, some of which can be propelled through the water by engines in the equivalent of about 120,000 horsepower, which produce all the thrust to drive, a 1,300-foot long ship through one propeller. Okay, so you're talking about all the power going into one device that has to be meticulously designed using fluid dynamics, or you're losing millions of dollars, right, in wasted fuel, slow transit times, etc. There's also, so I do experiments, clearly, but there's also a rich pedigree here at Iowa of simulation, computational fluid dynamics and modeling. This is work done by a colleague, Dr. Pablo Carica, also part of IIHR, looking at the flow around submarines as part of a Navy grant. My current area of research, what I'm working on right now, is amphibious vehicles. So actually, a little more on this next. I'll be out next week doing some experiments on this creation right here, which is this weird thing out of New Zealand. It's a four-wheeler that the wheels fold up into to become a jet ski. And I'm going to be running this through surf zone waves, so the waves close to shore where vehicles like this really have no business being. Okay, so I'm going to be actually off-site next week testing at the facility in the lower right, which is a 600-foot long tank of salt water out in New Jersey, where they're able to generate large waves, and I'm not sure if this video is going to play. Oh, there we go. Where they're able to artificially create waves using this giant paddle at the end of the tank. And I've got a student and myself have outfitted one of these vehicles with a whole host of sensors, everything to measure GPS position down to less than a centimeter, accelerations, gyroscopes, and thrust measurements to see how one of these vehicles performs in waves. So these are things I like to inject a little bit of my own research into my teaching. I hope that makes things a little more interesting for you. It certainly does for me. So if there are any people that are interested in water wave mechanics, ocean-going vehicles, or even amphibious vehicles, feel free to come chat with me. But my interests aren't the end-all be-all of fluid dynamics. As I said in the syllabus, this extends to everything, right? Every facet of life. from biology. Shown here is a case of what we call fluid structure interaction of a ray swimming. It's a case where, right, they have to swim by, propelling through the water. That means they're creating a load on the fluid, and the fluid's creating a load in response on the ray. But rays are very floppy. They're not very rigid creatures because they're so cartilaginous. And so as a result, they have to deform their fins in a way that they are efficiently working with the forces created in the fluid. Because if they just go flapping all willy-nilly, as some of our early robotic attempts try to do, they don't move forward. Sometimes they'll go backwards, sometimes they'll just spin around in place and look really dumb. To giant engineering structures, civil engineering structures like Grand Coulee Dam, right, which holds back, oh gosh, I had the number worked out. I'll get this for you in chapter 2, but just how many billions of gallons of water are being held back by this single concrete structure, right? If you ever flown in a plane and been unlucky enough to be just behind the wing in those really noisy seats, and you look out the window flying through clouds, you might see the generation of what we call wingtip vortices, right? These are present in anything that flies, whether it's above water or below water. To von Karman vortex generation. This is the pattern of clouds as it flows around a mountain peak. And this alternating swirling motion is something that we see in nature all the time, called a von Karman vortex street. And then finally, biomedical engineering, right? There's a huge facet of the same kind of fluid structure interaction I mentioned up here that goes on with circulatory flows, right? Blood pressure is not steady. It spikes. It goes through peaks and valleys. And with that, the elasticity of your blood vessels tends to cause expansion and contraction. So it's like flow through a pipe if all your pipes are made out of rubber. Okay. So we're going to talk about all of these to some degree. But before we do that, it's time to transition. Let's talk a little bit about some more fundamental questions. This is going to be the lecture format, by the way. Most of the lecture is going to be delivered, handwritten style, so it's easier for you guys to take notes. If we got videos or practice problems, I'll throw up PowerPoint slides. I also have this little dome up here, which is a microphone, and I'm recording the screen and audio for every lecture, and that'll all be posted on Icon. So if you guys need to go back and review stuff, there will be lecture videos that are actually what's being shown on the projectors on the screen. So, the things we want to actually cover today or the real questions we want to answer are, first, what is a fluid, right? What differentiates this from other types of sciences that we've studied? We want to cover how to the weight and mass of fluids, and we want to cover dimensions and dimensional homogeneity. So, fluid mechanics as a topic, right, is a branch of what we call continuum mechanics. Dealing exclusively with fluid substances. All right. Namely, we're interested in the properties of fluids, the forces exerted on object by a fluid and the reaction of a fluid to forces exerted on them by objects. All right. So these last two are kind of two sides of the same coin. All right. Force and reaction force. There are really two branches of fluid mechanics that we're going to cover in this class. First is fluids at rest. Which we know as fluid statics, and fluids in motion, which we refer to as fluid dynamics. So fluids at rest, or fluid statics, examples include things like some of the properties we discussed, right? Surface tension, or some of the properties that I mentioned above. We're interested in characterizing things like surface tension, density, weight, as well as the many engineering applications. Dams, for example, floating objects. These are all things that are governed by the forces that go on in a fluid when it's not actually moving. Fluid dynamics encompasses things like lift and drag, okay, the flow over objects, wing theory, and water waves. So we'll get into those more respectively, but the first half of the class, or the first third or so, is going to be dedicated to fluid statics. And then fluid dynamics is the broader topic that we'll be working on in the second part of the course. Okay, so I mentioned here fluid mechanics is a branch of continuum mechanics. Okay, continuum mechanics really has, it's got solid mechanics and it has fluid mechanics. Those are the two main divisions. All right, so fluids versus solids. Let's work out kind of what they share in terms of characteristics and how they differ. So fluids versus solids. How are they alike? Well, to begin with, both obey fundamental laws of conservation. These are the laws of nature that most of us know, even if we don't know that's what they're called. So examples include conservation of mass, right? If you take a rock, you put it on a scale, it weighs a pound, or you have a pound mass, then whether you heat the rock up, you cool it down, you smash it into a bunch of little rocks and weigh those pieces, you should always have 1 pound of matter. Okay? It's a simple idea that matter is not created, nor is it destroyed. With a fluid, things are a little bit more challenging because fluids tend to move around, right? Molecules don't all stick together. So we have a different expression for conservation of mass. Where for a solid, you might say that that the time rate of change of the mass of an object is equal to 0. For a fluid, you would say that the time rate of change over the integral of all the molecules that make up a bunch of fluid, okay, and you're integrating the density, it's equal to 0. So what this is essentially saying is, if you have a container full of, say, hydrogen, and you were to tag every single one of those molecules of hydrogen, and you were to let them go, if you were to later round them all up, the mass, the collective mass of those original molecules has not changed. So it's the same idea as with the solid, but we have to express it a little bit differently. And this is the case whenever we deal with fluids. That's why we need calculus in this class, is because everything turns into an integral. We have conservation of momentum. Which most of us know and love as Newton's second law, or F equals ma. Okay. And we have conservation of energy, which should be familiar to most of you from thermo. I guess, show of hands if you took thermo in the last semester. Okay. So we've got any folks that have not done thermo. Okay, so most of you have encountered the idea of conservation of energy before. The idea being that, right, the change in energy in a system is equal to the heat transfer into the system minus the work out of the system. Okay, we're going to get more into the fluids version of this in chapter 4 when we deal with control volume analysis. Okay, so we've got that fluids and solids are alike in that they both obey conservation laws. So this is characteristic number 1. Number 2, and this I'm going to abbreviate a little bit, is the idea that they are both continuum materials. Now what I mean by a continuum is that they obey what we call the Continuum Hypothesis. Right? We know that everything's made up of little bits of matter, right? Whether atoms or molecules, however you want to describe it. But take, for example, a case where we want to measure the temperature in a room. Okay, so I want you to think about a couple of different scales of how we do this, right? How big of a piece of matter, like how much volume of air in a room do we need to capture in order to measure the temperature accurately? Do we take a really, really tiny volume, something that's, maybe 1 micron by 1 micron by 1 micron? If that's the case, then we're going to have a bunch of individual molecules floating around, right? We know that temperature measurements occur because we have a little instrument that measures the kinetic energy of these molecules as they bounce around and hit our instrument. So if we were to measure the temperature, if we were to zoom in so far that we put our temperature probe right here between molecules, we might not see any reading because there are no molecules at that instant bouncing off of the probe, right? If we were to put our temperature probe right here, we would be in contact with a molecule at that precise moment, and we would see some reading, right? So the idea is that our measurement is dependent on molecule-to-molecule variation, right? Which suggests to us that we don't want to get this fine in how we characterize. We don't want to zoom in this far in terms of how we describe a fluid or a solid, for that matter. So instead, it's the reason that most physical instruments, if you go get a temperature probe, the end of that probe is going to be something about the size of the tip of a ballpoint pen. Okay. So let's say it's a cubic millimeter in size. A cubic millimeter contains about what's the number here? About that many molecules of a typical fluid, a gas even. So the idea is, if we're looking at a volume of fluid and an extra molecule enters, it's not going to matter. It's 1 part in 10 to, I don't even know what to call that, 10 to the 21st. Okay? So it is so little molecule to molecule variations don't matter. But that 1 cubic millimeter is a small enough volume that we can treat it as effectively a point in space. So the whole gist of the continuum hypothesis, as we call it, is that we can forget about the molecular level variations. And we can say, if we have a point in space, x, y, z, okay, that describes a physical place, we can describe the properties of a fluid at that point, rather than worrying about the properties of the individual molecules that are down at the molecular scale at that point. Okay. This is as opposed to things like multi-body dynamics. If you're considering what happens when you throw a basket full of ping pong balls into the air, that's very different. You have to account for the individual trajectories and forces on each ping pong ball. In this case, we worry about what goes on at points in space. So both fluids and solids obey this continuum hypothesis. Okay, fluids and solids, how do they differ? Well, there are the obvious components, such as their tendency to retain shape, right? If you take a solid, they retain their shape and their volume. When placed in the container, you take a rock, you throw it in a bucket, you still have a rock. Right? Fluids assume the shape of their container. Okay. You take a gallon of water and you pour that into the bucket. It looks like a bucket with a rock-shaped hole in it. If you take a gas, you have the further case where it will expand to fill the volume. These are all review concepts, I'm sure, from chemistry and thermo. But we have this idea of shape retention. This has a lot to do with the real difference that I want to get across, which is the difference in what we call the constitutive laws. So the reason this occurs, the reason we have fluids that assume the shape of whatever their container is that fluids cannot sustain shearing stresses without motion. Okay. Whereas solids can. Solids obey this law that we call Hooke's law. So if you take a block of material, okay, and you apply a shearing force to it in this direction, what's going to occur is that block will deform by some amount, okay, but then it'll reach a static equilibrium. So this is known as Hooke's law, and it says that stress is proportional to strain. Okay. Now, from solid mechanics, the other continuum mechanics classes, we know that there's things like the shear or Young's modulus, right, that describe this proportionality. For fluids, however, it's a different story. If we take a film of water, let's say we've got a film of water here sitting over the top of a flat plate, and we were to somehow apply a shearing force to this film of water, is it going to move a little ways and then stop, or is it just going to continuously flow? Okay. Think about what happens when you're pulling a water skier behind a boat. Okay. You don't have to keep throttling up further and further and further as the water skier gets further from your starting position. What happens is you hit a constant throttle position, it's pulling with, I don't know, let's say, 200 newtons of force on the water skier, and they're continually moving along the surface of the water. So what that's doing is it's causing this shear deformation of the water. So what's going to occur instead of this static deformation of the solid is we're going to get a case where the water flows with some velocity distribution. Newtonian relationship. So this is something we're going to cover in more detail in the next lecture, but it's important to note this, that the stress in a fluid, rather than being related to strain, is related to what we call the rate of strain. So with these ideas, right, what makes solids and fluids similar and what makes them different, we're prepared now to really define what a fluid is. So let's go ahead and state here a definition of a fluid, which is a continuum material that deforms continuously under an applied shear stress. Write that down. That's one of the few memorize this moments that we're going to have in this course. So we've defined what a fluid is, what the study of fluid mechanics entails. Now let's talk about some of the nitty-gritty. Dimensions and units. Okay. So when we're talking about any physical science, right, we've got these two kind of flavors of descriptors. Dimensions, which are the qualitative measure or type of measure in which a quantity is expressed. And we have our units, which are quantitative choices about how or how many or how much try the phrasing here. Yeah, that's across. So what I mean here is if we ask you, right, how far is it to Chicago? What kind of answer are you going to give me? Okay, are you going to say 3 degrees Fahrenheit? No, right? You're going to say, well, it's 250, 300 miles. That is a expression of length, right? So the dimension that we're using here is length. What would you use to measure it? Something that measures length or distance. The choice of how many miles or kilometers or inches or angstroms is our choice of units. Okay? So this is the more fundamental of the two, the dimensions. Because any physical quantity can be expressed in terms of 4 basic dimensions. We've got mass, length, time, and theta here, which stands for temperature. Okay. So the idea is whatever kind of quantity you come up with, we can break it down into a product or quotient of these 4 units of measure, or these four dimensions. The choice of units that we use to describe those the actual specific quantities are not important for this stage. So, for example, if we're interested in finding the dimensions of a distance from point A to point B, the idea is, as I already said, this is a measure of length, right? At its most fundamental level, and so we would say this we describe the dimensions of this measure using the length nomenclature in square brackets. Okay. If we wanted area, well, an area is a length times another length, right? So we'd end up with length, or L squared, square brackets. Similarly, volume would be length to the third power. What about a speed? Someone want to hazard a guess? Right. You've got L, length traveled per unit time, right? Or length time to the negative 1. Let's try acceleration. Okay. Acceleration, right? It's going to be, if you think about the units, like meters per second squared, feet per second squared, it's length divided by time squared. So up with L, T to the negative 2. What about force? What is Newton's second law? What does Newton's second law say? F equals ma. That is a mass times an acceleration. Okay. Well, mass is one of our 4 basic dimensions. Acceleration we've got right here. So we simply multiply those two, and we end up with mass, length, time to the negative 2. Yeah.
How would you represent like brightness? Isn't
Represent what?
brightness?
Brightness?
Yeah, don't you use lumens for that?
So that's a specific
Its own
unit. So that's a good point. Things like radiance and brightness, these are typically measures of energy, okay, or energy per unit area. And energy can be thought of as force, right, or mass, velocity squared. And so you can still boil it down to these basic dimensions, right? Example, pressure. Okay, pressure is a force distributed over an area. So we could take our force there, divide by our units for area, and we're going to end up with mass, length, negative 1, time to the negative 2. Okay, so I'm going to stop beating you over the head with these. But there's an important thing to take away here, is that just like you can't add apples and oranges, right? You can't add quantities that have dissimilar dimensions. So this brings us to this really important thing we call dimensional homogeneity, which essentially says we're coming up here in the end of class. Dimensional homogeneity says that anytime you have A plus B, right, A and B have to have the same dimensions if you write them out like this, right? Units, less important, right? If A is in meters and B is in inches, you can do a conversion there. But if A is in a unit, or is in dimensions of mass, and B is in dimensions of temperature, then they simply cannot add them. Similarly, C has to share the same dimensions. So the idea is any time that there's a plus sign or an equal sign, the dimensions of every quantity between those signs, or across those signs from one another, have to be equal. So as a quick little, one last little example here, before I give you the last slide of information. Let's say that the drag on a building, right? We've got a building out in some, say Chicago, where the wind drag or the wind force on that building is important, right? The architects and structural engineers want to make sure it doesn't topple over. And the way you measure the force of wind on that building is by the product of what we call the drag coefficient times density times velocity squared times area the projected area of building. Okay. So looking at this, let's try to find what the dimensions are of this drag coefficient. Okay. So using the expressions we had before, right, in that force on the left-hand side, density, which is going to be, I'll leave it to you guys, but mass over the volume. Okay, velocity squared, area. We've got everything except density and drag coefficient already in this list. And so if we solve for the drag coefficient in this expression, CD, right, is equal to F over rho V squared times A. We wrote out the dimensions of each of these terms, okay, where it's going to be equal to mass, length, time, -2, length to -2, 1, length. Okay. We've got each of our terms with the associated dimensions, and we just went through and started scratching out exponents. What we would find is that we've got a mass to the first, mass to the negative first. Those cancel out. Length, length to -2, length cubed, length to -2. That ends up being a length cubed times length to -3, so those all cancel out. We've got time to the -2 and time squared. So those guys cancel out. So what we end up with is mass to 0, time to the 0, which means it doesn't have any dimensions. This is what we call a dimensionless quantity. These are going to be really important in fluids. But I wanted to point this out because I think there's a problem dealing with dimensionless quantities in the first homework. And so if you manage to find that you've canceled out all the dimensions when you're looking at an expression, it doesn't mean you've made a mistake. It might mean that you've got one of these quantities that doesn't have length, mass, or time, or temperature associated with it. So we are out of time. In the last, we've got like 40 more seconds. Hold on. There's one last thing that I want to point out. This is the way we define density, specific weight, and specific gravity. This is very simple, and most of you have seen this before, but the idea is for density, we describe this using the variable rho, and this is a mass over a volume. Specific weight is the gamma, which is weight over volume, which is simply equal to gravitational acceleration times rho. And specific gravity we describe as SG, and this is the density of an object or of a material divided by the density of water at 4 degrees Celsius, which ends up being over 1,000 kilograms per meter cubed. Okay, so the idea with density is how much does it weigh per unit volume, specific weight, or sorry, how much mass per unit volume, how much does it weigh per unit volume, and how much does it weigh, or how mass is it compared to an equal quantity of water. Right. So with that, I'll turn you guys loose. I'm going to post the first homework immediately after I get back to my office, and I'll see you guys on Wednesday.
I just wanted to make sure we didn't have lab this week.
No, we don't have lab this week. Thanks for reminding us. I didn't get back to the lab schedule.